Hello, today I'll be presenting on the fundamentals of battery materials, focusing on synthesis, structure, and properties from an inorganic chemistry perspective. Battery technology and efficient energy storage are imperative as humanity transitions to renewable energy sources. As inorganic chemists, our understanding of material properties and how they relate to structure is crucial for advancing this field. Over the next 25 minutes, I'll cover three main areas. First, we'll explore the various synthesis methods used to create these materials, from traditional solid-state approaches to cutting-edge nanomaterial fabrication techniques. The way we make these materials directly impacts their performance. Second, we'll examine the critical structural features of battery materials, how atoms arrange themselves in crystals and how these arrangements create pathways for ions to move. Structure is the foundation upon which all battery properties are built. Finally, we'll connect these structures to their properties, exploring how the atomic level arrangements determine real-world performance like capacity, voltage, and cycle life. Understanding these fundamentals is crucial not just for academic knowledge, but for addressing practical limitations in current battery technologies. The materials challenges we face, improving energy density, extending lifetime, enhancing safety, and reducing costs, all require a deep understanding of these underlying principles. This topic combines fundamental chemistry with practical applications that directly impact our sustainable energy future. Battery basics, structure and components. Let's start with the fundamentals of how batteries work. Batteries consist of two electrical terminals called the cathode and the anode, separated by a chemical material called an electrolyte. To accept and release energy, a battery is coupled to an external circuit. Electrons move through the circuit, while simultaneously ions move through the electrolyte. This is the basic principle of all batteries. They store energy in chemical bonds and release it through controlled redox reactions. What makes battery chemistry so fascinating from an inorganic perspective is how the atomic and molecular structure of these materials directly impacts performance. Importance of materials, science in battery development. Synthesis is critical not only to the generation of new materials for exploration of new structures and fundamental properties, but also for the formation of materials with the optimum electrochemical behavior for commercial devices. The materials we choose determine everything about battery performance: energy density, how much energy can be stored, power capability, how quickly energy can be delivered, cycle life, how many times the battery can be charged/discharged, safety, thermal stability. Reactivity. As we'll see throughout this presentation, the way we synthesize materials directly impacts their crystal structure, which in turn determines their electrochemical properties. Solid-state synthesis. The traditional approach to synthesizing many inorganic battery materials, particularly cathodes, is solid-state synthesis. This method involves mixing precursors, typically metal oxides, carbonates, or other salts, and heating them at high temperatures, often 600 to 1000 degrees Celsius, to promote diffusion and reaction. For example, to synthesize the common cathode material Li2Co, we might mix Li2Co3 and Co3O4 in a stoichiometric ratio and calcine at around 800 to 900 degrees Celsius. The reaction proceeds through the decomposition of the carbonate, releasing Co2, and the subsequent formation of the layered oxide structure. Solid-state synthesis offers several advantages. It's well established, scalable, and can produce highly crystalline materials. However, it also has limitations: high energy consumption, limited control over particle morphology, and potential volatilization of certain elements during high-temperature processing. Recent advances in solid-state synthesis include innovations like co-doping strategies. For instance, research has demonstrated that Sr² plus and Tar5 plus co-dope Li0.5 La 0.5 x SrXT1 x Tar XO3 perovskites synthesized by solid-state reaction showed significantly improved ionic conductivity compared to undoped specimens. The co-doping approach used larger ionic radius elements to increase the bottleneck size of migration pathways, thereby enhancing lithium-ion mobility through the structure. Mechanochemical synthesis. often implemented through high-energy ball milling, uses mechanical energy to initiate chemical reactions. This approach has become particularly important for sulfide-based solid electrolytes, which typically can't withstand high-temperature processing. In a typical process, precursor materials are placed in a milling jar with grinding media, and the mechanical impacts provide the energy needed for reaction. For example, Li3PS4, an important sulfide electrolyte, can be synthesized by milling Li2S and P2S5 in appropriate ratios. The advantages of mechanochemical synthesis include room temperature processing, elimination of solvents, and the ability to create materials that might decompose at elevated temperatures. Additionally, the high-energy impacts can introduce defects and amorphous regions that sometimes enhance ionic conductivity. However, challenges include potential contamination from milling media, difficulty in scaling up, and limited control over the exact defect structure introduced. Solution-based methods. Solution-based synthesis approaches include sol-gel, co-precipitation, and hydrothermal/solvothermal methods. These techniques generally offer better control over particle size, morphology, and homogeneity compared to solid-state methods. In sol-gel synthesis, precursors like metal acetates or nitrates are dissolved in a solvent with chelating agents to form a gel, which is then dried and calcined. Co-precipitation involves the simultaneous precipitation of multiple metal ions from solution, typically followed by filtration, drying, and heat treatment. Hydrothermal synthesis uses water under pressure at temperatures above its boiling point in a sealed vessel, creating conditions for crystallization from solution. These methods typically allow for lower processing temperatures than solid-state synthesis, which can reduce energy consumption and prevent undesired high-temperature phase transformations. They also enable precise control of stoichiometry and can produce nanoscale particles with high surface area. For example, Li-FePO4, an important cathode material, can be synthesized hydrothermally using iron sulfate, phosphoric acid, and lithium hydroxide at temperatures as low as 150 to 200 degrees Celsius, resulting in well-controlled morphologies that improve electrochemical performance. Advanced synthesis techniques. NRL has developed innovative approaches including atomic layer deposition, ALD, for applying conformal thin film coatings to highly textured surfaces. These coatings have been shown to enhance cycle life and abuse tolerance in Li-ion batteries by mitigating deleterious side reactions and preventing mechanical degradation. Other advanced techniques include creating crystalline nanotubes and nanorods to address thermal management, weight, and conductivity issues in batteries. Now let's look at how the crystal structures of these materials impact battery performance. Cathode materials, structures and properties. Cathode materials can be broadly categorized into three major structural types: layered, spinel, and olivine structures. Each offers distinct advantages and limitations. Layered structures, exemplified by Li-Cu2 and other LiMo2 compounds, where M can be Ni, Mn, Co, or combinations thereof, consist of alternating layers of lithium ions and transition metal oxide sheets. The transition metals occupy octahedral sites in a close-packed oxygen lattice, forming Mo2 sheets between which lithium ions reside. This layered arrangement creates two-dimensional pathways for lithium ion diffusion, which enables relatively fast ion transport. However, the structure can become unstable when too many lithium ions are removed during charging, causing oxygen layers to collapse or shift. This structural instability limits the practical capacity of many layered oxides. For instance, Li-Cu2, the first commercially successful lithium-ion battery cathode, has a theoretical capacity of 274 mAh/G, but practically, only about 140 mAh/G can be utilized to prevent structural collapse. Newer layered materials like NMC, Li-Nix-Gamma-Co-KO2, and NCA, Li-Nix-Go-Gamma-Al-KO2, aim to address these limitations through compositional engineering. Spinel structures, represented by Li-Mn2O4 and similar compounds, feature a three-dimensional framework where lithium ions occupy tetrahedral sites and transition metals occupy octahedral sites in a cubic close-packed oxygen lattice. The three-dimensional network of channels allows for lithium-ion diffusion in multiple directions, typically resulting in better rate capability than layered structures. The spinel framework is generally more stable during cycling than layered structures, but manganese-based spinels can suffer from manganese dissolution, especially at elevated temperatures, leading to capacity fade. Modifications like partial substitution of manganese with nickel or strategic doping can mitigate these issues. Olivine structures, with Li-FePO4 as the prototypical example, have a different architecture altogether. In this orthorhombic structure, iron occupies octahedral sites, phosphorus forms tetrahedral PO4 groups, and lithium ions reside in one-dimensional channels along the O1O direction. The strong covalent PO bonds in the phosphate groups provide excellent structural stability and thermal safety. However, the one-dimensional nature of lithium-ion diffusion means that any defects or impurities can block entire channels. Additionally, the electronic conductivity of olivines is typically poor, necessitating carbon coating or nanostructuring to achieve good performance. Despite these challenges, Li-FePO4 offers exceptional cycle life and safety, making it valuable for specific applications. Anode materials, structures and properties. Turning to anode materials, the structural diversity is equally rich, with mechanisms ranging from intercalation to alloying and conversion reactions. Graphite, the most common commercial anode material, consists of stacked graphene layers held together by weak van der Waals forces. During charging, lithium ions intercalate between these layers, forming staged compounds like Lic-6. The staging phenomenon, where lithium ions organize in specific patterns between graphene layers, helps minimize repulsion between ions. The intercalation process causes only modest volume expansion, 10%, and occurs at a low potential versus lithium, 0.1 volts, both desirable properties for an anode. However, graphite's theoretical capacity is limited to 372 mAh/G, prompting the search for higher capacity alternatives. Silicon represents one such alternative, with a theoretical capacity of 3579 mAh/G, nearly 10 times that of graphite. Unlike graphite, silicon undergoes an alloying reaction with lithium, forming various Li-16 phases. This alloying mechanism allows for much higher lithium storage capacity but comes with a significant challenge: volume expansion of approximately 300% during lithiation. This massive volume change leads to particle pulverization, loss of electrical contact, and continuous electrolyte decomposition on freshly exposed surfaces. Strategies to address these issues include nanostructuring, composites with carbon, and specialized binder systems. Transition metal oxides offer another structural paradigm for anodes, operating through conversion reactions. As highlighted in Knoll's research, materials like molybdenum oxide and iron oxide can achieve capacities significantly higher than graphite. In conversion reactions, the metal oxide is reduced to metal nanoparticles dispersed in a lithium oxide matrix during lithiation. Solid electrolytes, crystal chemistry. The crystal chemistry of solid electrolytes is particularly fascinating, as it directly determines ionic conductivity, the key property for these materials. Garnet-type structures, exemplified by Li7La3Zr2012, LLZO, have emerged as promising oxide-based solid electrolytes. In this structure, lithium ions occupy tetrahedral and octahedral sites within a framework of 0,6 octahedra, and Lao-8 dodecahedra. The cubic phase of LLZO, typically stabilized by aluminium or gallium doping, offers three-dimensional pathways for lithium-ion conduction. What makes garnets attractive is their combination of reasonable ionic conductivity, 10-4s/cm at room temperature, wide electrochemical stability window, and compatibility with lithium metal. However, challenges include high grain boundary resistance and poor wettability with electrode materials. Sulfide-based electrolytes like Li10Jet2s12, LGPS, and argyrodites, Li6PS5X, where X is a halide, offer even higher ionic conductivities, approaching or exceeding those of liquid electrolytes. The LGPS structure features one-dimensional channels formed by PS4 and GES4 tetrahedra, creating a framework with exceptionally fast lithium-ion transport. Argyrodites represent another fascinating structural family, where partial sulfur substitution with halides enhances conductivity. In Li6PS5Cl, for example, the chloride ions occupy specific sites in the sulfur sublattice, modifying the lithium-ion potential energy landscape to reduce migration barriers. The higher conductivities of sulfide electrolytes compared to oxides can be attributed to the more polarizable nature of sulfur compared to oxygen, resulting in weaker interactions with lithium ions. However, sulfides typically have narrower electrochemical stability windows and are sensitive to moisture and air. Perovskite and Nazikin-type structures represent additional structural families with promising properties. The perovskite Li3X La2/3XTO3 features an ABO3 structure with lithium and lanthanum sharing the A site, and titanium occupying the B site. The presence of A-site vacancies creates diffusion pathways for lithium ions. Understanding these diverse crystal structures and their ion transport mechanisms is essential for designing improved solid electrolytes that can enable next-generation solid-state batteries. Structure-property relationships. How structure affects ionic conductivity. In some studies, researchers have used Sr² and Tar5+ with larger ionic radii for co-substitution in the La3+ and T4+ sites to increase the bottleneck size in perovskite structures, thereby expanding the average bond length and increasing Li+ ion mobility. How synthesis influences structure. The synthesis methods influence inorganic solid electrolytes in terms of phase structure, ratio of amorphous phases, strain, defects, grain size, grain boundary resistance, impurities, and morphology, thus critically determining their performance in batteries. Structural stability during cycling. A major challenge in battery materials is maintaining structural integrity during repeated charging and discharging cycles. Materials that undergo significant volume changes or phase transitions often show rapid performance degradation. Advanced characterization techniques. Understanding battery materials requires sophisticated characterization methods. Characterizing battery materials requires sophisticated techniques that can probe structure, composition, and properties across multiple length scales. Let's briefly explore the key methods used to understand these complex materials. Ex situ characterization. Synthesized materials and electrodes are first characterized by various ex situ techniques like electrochemical tests, diffraction, and NMR to gain information on phase purity, structure, and physical properties. In situ and operando methods. Advanced characterization such as in situ methods provides a further level of detail regarding device behavior. Both in situ and operando measurements allow insights into fundamental chemical and structural properties under working conditions, including dynamics and metastable phases that are often not detectable in ex situ approaches. Material properties for battery performance. Electronic properties. The electronic conductivity of battery materials is critical, especially for cathodes and anodes. Many active materials have poor electronic conductivity and require conductive additives or coatings. Electronic properties. The electronic conductivity of battery materials is critical, especially for cathodes and anodes. Many active materials have poor electronic conductivity and require conductive additives or coatings. Mechanical properties for polymer electrolytes. The concept of a material that acts as both the physical separator and the electrolyte while maintaining good contact with the electrodes through many charge/discharge cycles has motivated research for over 3 decades. Case studies, material design strategies. High-energy cathode materials. Ni-rich cathode materials have been developed to increase energy density, but they face stability challenges that require creative solutions like surface coatings and elemental doping. Silicon-based anodes. Silicon anodes are being investigated by the Silicon Anode Consortium as a possible viable alternative to graphite due to their much higher theoretical capacity. However, They face challenges related to volume expansion during cycling. Fast ion conducting solid electrolytes research has demonstrated that high ionic conductivity exceeding that of liquid organic electrolytes can be achieved in non-oxide inorganic solids. These materials are enabling the development of all solid-state batteries. Future directions and challenges. As we look to the future of battery materials, several promising directions and persistent challenges warrant attention. Next-generation battery technologies. Solid-state batteries hold the promise of providing energy storage with high volumetric and gravimetric energy densities at high power densities, with far fewer safety issues compared to conventional batteries. Materials design principles. Moving forward, rational design of electrodes and solid electrolytes must thoroughly exploit the interplay between composition, crystal structure, and electrochemical properties. Multivalent ion batteries based on magnesium, calcium, or zinc offer the potential for higher energy density through multiple electron transfers per ion. However, finding suitable electrode materials and electrolytes for these larger, more strongly interacting ions presents significant challenges. The fundamental understanding of multivalent ion insertion mechanisms and transport remains less developed than for lithium systems. As we've explored throughout this presentation, the fundamentals of battery materials, synthesis, structure, and properties, are deeply interconnected. The way we synthesize materials determines their structural features, which in turn govern their properties and performance. Understanding and manipulating these relationships is the key to advancing battery technology. The field of battery materials is at the intersection of inorganic chemistry, solid-state physics, electrochemistry, and materials science. This interdisciplinary nature makes it both challenging and intellectually rich. The principles we've discussed today, from crystal structure determination to ion transport mechanisms to interface engineering, represent the foundation upon which practical battery advancements are built. Looking ahead, the continued development of battery technology will require innovations across multiple fronts: new materials with enhanced properties, sustainable synthesis methods, advanced characterization techniques, and computational tools for materials prediction. The most significant breakthroughs will likely come from approaches that integrate these different aspects, connecting fundamental understanding with practical applications. Thank you for your attention. I hope this presentation has provided a useful overview of the fundamentals of battery materials and their critical importance in advancing energy storage technology. Here are the list of references and sources.